Abmeldungen hatten. Normalerweise haben wir am Tag 10 Anmeldungen, aber vielleicht müssen die Leute Fußball gucken oder sowas. Es regnet, genau. IoT Vienna hat sich nicht nur zur Internet of Things Gruppe in Wien entwickelt, sondern entwickelt sich auch zu der Internet of Things Gruppe in Österreich. Das merken wir in letzter Zeit immer häufiger durch die Rückmeldungen, die wir haben. Ihr werdet das nachher auch an den Speaker sehen für die nächste Veranstaltung. Ob das jetzt das Institut für Technologiefolgenabschätzung ist, ob das Austrian Institute of Technologies ist, ob das die Universität hier in Wien ist oder in Graz und Linz, die einfach Interesse an unserer Gruppe haben und als Teilnehmer bzw. als Speaker sich beisteuern wollen. Internet of Things ist natürlich ein riesiger Bereich. Ich habe mit dem Herbert Dirnberger gerade ein bisschen darüber diskutiert. Das kann sein Wearable Technologies, das kann sein Industrie 4.0, Smart Home Automation, Gebäudeautomatisierung, in der Landwirtschaft, im Gesundheitswesen, aber auch solche Sachen wie jetzt zum Beispiel Big Data, Augmented Realities, Verkehr, Auto, Infrastruktur, überall ist gerade das Thema Internet of Things. Wie bringe ich das da irgendwie an? Wie kann ich da einen Vorteil draus ziehen oder bringt es mir ein Nutzen? Diskussionsthema. Und wir merken, dass das in der Industrie ein riesiger Bedarf da ist, sich einfach über dieses Thema zu informieren. Als erstes möchte ich unseren Sponsoren danken. Pflicht. Diesmal ein bisschen kürzer. O'Reilly sponsert uns mit ein paar Büchern über International Systems, vertreten durch Herrn Professor Dr. Robert Barter. Die Firma Pompadour IT Solutions aus Deutschland, die werden im November mit dabei sein. Eine sehr interessante Software zur Management von ganzen Wartungsprozessen, zum Beispiel Gebäude oder Kälteanlagen oder Industriegüter, die ganzen Wartungsprozesse ein bisschen zu strukturieren. Das Stockwerk, natürlich, die uns diesen wunderbaren Raum zur Verfügung stellen. Alexander hat mir gerade gesagt, wenn ihr Interesse habt, hier euch einen Arbeitsplatz zu nehmen, die ersten 3 Monate gibt es für User von IoT Vienna bzw. von Freunden von IoT Vienna 25% Nachlass. Meldet dich schnell an, jemand bis 25% weniger. OS Domotics stellt uns die Organisationsstruktur zur Verfügung, Cox-Tun, die Macro-Boards und der Club, Helmut ist wieder dabei, zum Füllen. Wenn ihr auch Sponsoren werden wollt, es hält euch nicht davon ab, unsere Events mitzufinanzieren, dass wir das einfach ermöglichen können. Jeden Monat euch Talks auf einem recht hohen Niveau anzubieten und jeden Monat euch Workshops anzubieten, wo ihr das, was wir in den Talks an Technologien vorstellen, auch wirklich mal selbst ausprobieren könnt. Wir brauchen ein bisschen Hilfe von euch, denn die Organisation von IoT Vienna ist schon recht zeitintensiv. Und was wir als erstes brauchen, ist so jemanden hier. Jemanden, der uns im Marketing unterstützt. Einfach die Gruppe populär zu machen, dafür zu sorgen, dass in der Meetup-Szene in Wien die Leute uns kennen, dass wir jetzt zum Beispiel im Industrie 4.0-Bereich an die entsprechenden Leute herankommen, im universitären Bereich an die Leute herankommen. In vielen Bereichen passiert gerade viel und wir wollen die gerne alle zusammenbringen, dass man miteinander etwas machen kann. Was wir auch brauchen, ist ganz klar ein bisschen Kleingeld. Es wäre super, wenn ihr da vorne beim Lennart an der Bar ein bisschen was einwerfen könntet, um unsere Arbeit zu unterstützen. Lennart ist übrigens der Held des Tages, weil Lennart ist derjenige, der euch heute mit Snacks und Getränken versorgt. Wenn ihr Durst habt, geht hin zum Bahnhof für euch. Okay, die IoT Talks Oktober 2014. Als erstes hier das Muster. 20 Minuten Vortrag, 10 Minuten Q&A, 10 Minuten Pause. Okay? Und ich gucke auf die Uhr. Agenda für heute ist, Gösta wird anfangen, wird eine Einführung geben in IPv6 für IoT-Devices. gefolgt von Daniel Amesberger von der Messcom, Electronic Product Development, Steps on how to single-handedly build your own IoT device. Also schauen die Prozessschritte aus, wenn ihr ein eigenes IoT-Device entwickelt wollt. Dann Johannes Tinsobin von Atheneum wird sprechen über IT-Business-Modells. Er wird gemeinsam mit uns das im Rahmen eines interaktiven Workshops gestalten. Und Robert Barter, Don't Be an Aliat, Identity Management for IoT with Semantic Networks. Nach den Talks nicht weglaufen. Und wir haben die Chance, hier zu bleiben und über die Themen, die in den Talks drangekommen sind, auch zu diskutieren. Wir können den Raum so lange nutzen, bis die Augen zu machen. Okay? So, fangen wir an. Gösta als erstes. Applaus für Gösta.
Okay, I was asked to give this talk in English, recording, and because of the guests who don't understand German too well, there are one of them here. Should I continue?
Continue in English.
Okay.
They will come in about 10 minutes.
Okay, fine. So, two apologies are necessary. Of course, I'm not a native English speaker, so my English might become a bit clumsy after so many hours working today. The second one is there are lots of slides and I will rush through them because I did the talk with these slides for a duration of 1 and also for 6 hours. And I was asked on Friday, Saturday to jump in for a speaker who could not hold his speech tonight, so I had no time to reduce them to reasonable size. So, enough of this. 2 sentences about me. I'm a child of the early 1970s, so my first contact with computing was in the 80s. My first contacts with IP networking, web networking, in the early 1990s. I did IPv4 then, of course, but I could have soon after started with IPv6 if I had known about it then. And it will be quite a tall order for me to sum up the things that took the whole internet 20 years to accommodate within 20 minutes of talk. I will try and do my best. Okay, well, the slides are from, of course, from OS Domotics, and were given for a networking basics workshop. So here's a short intro. How does IPv6 come into the Internet of Things context? And on the Smart SARA stack for smart home automation systems. In the network layer, we use IPv6 because of, as I will show in a few minutes, because of the vast address space available and the surprisingly small header size of the packets. So with small devices, and in computing terms, even your refrigerator is a small device, it's quite handy to use those IPv6 addresses and packets because they are easier to calculate. Okay, short review. IPv4 was the first internet protocol largely used and to interconnect networks. It was the first protocol to guarantee endpoint-to-endpoint communication in computer networking. It provided an address space of billions of IP addresses, which seemed enormous in the 1980s, but they are quite short nowadays. So the first shortcoming of the old protocol stack is this addressing scheme, which allows only about a few billions of addresses globally reachable. The second shortcoming is, I will jump what's this? The second shortcoming is security. When IPv4 was designed, computer security was not a major concern. Computing was something only conducted in big businesses and universities, and everybody was friends then, so who cares about networking and data security? Anything we know today, like firewalling, like IP, VPN networking, and SSL encryption are backports. The IPsec actually is a backport from IPv6 to IPv4, so it was not developed for IPv4 networking. The big problem though was that sometime in the 1990s, the addressing scheme of IPv4 reached its limits. The growth of the internet was so vast that the local networks had to use locally administered addresses, and we all know them very well nowadays. It's the scheme 10.00 whatever, or 192, 168, whatever. And there are some network translation devices which translate those internally used network addresses to externally routable devices. But this was the end of end-to-end communication, because nowadays we got lots of hosts using the same locally administered addresses, and they can impossibly talk to each other across the internet. This is a slide you could study at home. This illustrates the unequally distributed availability of IPv4 across the globe. So, what is this IPv6 thing now? As I already said, we get a vast address space, which means we got very, very long addresses. And they started designing IPv6 at about 20 years ago. And the idea was, we did it wrong with IPv4 address space, so this time we will do it right, and we do it properly right. The address space is now 128 bits long, which is today's internet multiplied by today's internet multiplied by today's internet multiplied by today's internet, which gives billions of billions of billions of billions of addresses. Usually addresses are written in this human readable form of 4-digit hex parts divided by colons. And you can see here, those things can grow pretty long. This is not very handy for human use, so there are some simplifications allowed. You can strike out any leading zeros, reducing the length of the address dramatically. And you can strike out continuous blocks of zeros, replacing them by a double colon sign. This leads to an ambiguity, as I showed in this lower address here, where you have two ranges of zeros. If you replace them both with double colons, it's impossible to decide where to fill in the 0 bits by reconstructing the address. So usually you just reduce the long apart, and but you can, of course, take out the leading zeros here. This still doesn't lead us to very human readable addresses, and there are also some RFCs describing ways to translate them to pronounceable addresses. One of them started as a hope scheme. It is called banana, which translates those parts into spellable syllables, where your servers get quite funny spelling IPv6 addresses. Okay, so If you're familiar with IPv4, you of course know the concept of subnets and the concept of the subnet names, the net mask name. This is a concept also used in IPv6, but of course subnets are greater and subnet masks are of course wider. Typical IPv6 subnet consists of 2 to the power of 64 hosts. So the subnet length is 64-bit, and the first 64-bit consists of the subnet identifier, and the second half is used for the host identifier. So as we do with IPv4 with CIDR addresses, /24, /16, notation of the subnet size, we do here with IPv6 only with higher numbers. If you register a IPv6 address range at your ISP, you will typically get a /64 subnet for home use, for private use, where you can build in your own internet by the internet number of hosts, so you can literally give any leaf of your plants an IP address and will never run out of space, even if you're a farmer. If you're a company, you usually get the 56 or 48-bit long prefix length, where you can build thousands of subnets within this range. So the chances are good that we will overcome IP shortage for a couple of years from now. Okay. Well, if you ever looked at the IP configuration of your Linux, Windows, Apple host in an IPv6 enabled network, you might have realized there are more than one IPv6 addresses per link, per network interface. This is because there are several address types which have specific meanings in IPv6 terms. First one is the link local address, which is only valid on the local subnet. This address is used to talk to other hosts on the same collision domain in Ethernet talk on the same subnet. So if the client wants to reach its router or the local printer, they communicate with each other via addresses starting with FE80, and then there are some stuffing bits and the host part. This is also used for the auto configuration of the network, which I will cover in a few slides. And then there's another thing, quite interesting. As I mentioned before, nowadays we use locally administered addresses in our IPv4 ranges, specified in RFC 1918. And the similar scheme was designed for IPv6, formerly called the site local addresses. Nowadays it's called unique local IPv6 unicast addresses. It's quite cumbersome name, so excuse me if I fall back to site local frequently. The scheme works with a prefix of FE00, and then there are 40 bits of random ID you can generate for yourself, and a 16-bit subnet and a 64-bit interface address. So you also get 2 to the power of 16 subnets to handle for yourself. But also, like the RFC 1918 addresses, these addresses are not globally routable. So what are they for? If you don't want to register a public, globally routable IPv6 subnet for any kind of reason, say paranoia, or your ISP isn't able to provide one to you, but you want to interconnect sites together with a virtual private network or some other tunnel technology, and you want to avoid collisions between the networking schemes, you could use these. But nowadays it's quite easy to get IPv6 subnets from ISPs, even from home use ISPs or low-cost ones. Okay, so the officially used, the globally routed IPv6 addresses also all start with 200. It's not 2000 because it's decimal value. And there are divided into some subnets which are more or less historical. Teredo is a tunnel broker system where you can interconnect IPv6 networks across IPv4, across the legacy internet backbone. This is the range you should use if you write slides, documentation for IPv6, and you don't want to use real globally routable IPv6 addresses. Any reasonably configured router will just drop packets going to the 28 subnet. This is also historically, 64 is quite still in use. It's one of the transition techniques to bring the IPv4 internet to the current century. One of the great improvements by using IPv6, besides the vast namespace, is the ability to auto-configure the network. And this is done by some magic prefix and host presets. First of all are some multicast addresses, like the all nodes. I come to this later. All nodes, all routers, multicast addresses. And there's also a nice scheme called the anycast address. You could compare it to a situation when, if I want to talk to any one of you specifically, it would be a unicast conversation. I would face you and ask you a question, and get the idea. If we talk as a group together, that would be multicast. But if I say, could anybody tell me the time? And I'm happy with the first answer I get from anybody, this would be an anycast conversation. So if I want to talk to any of the available time servers to get the network time, which I don't care who delivering it to me, I can use this anycast address. So this is a new feature which is quite handy for configuration of standard internet services. You can use multicast depending on the scope. I will not go into details. There are some interesting multicast groups, especially for self-configuring networks, which is very interesting in the Internet of Things context, because I don't want to go configuring any single handle on my heating system to connect to the rest of the system. All nodes are addressed by FFO, whatever scope I want to do, and 1 on the end. All routers with the 2, or the time service interval example from I just mentioned. We'll take this address, for instance. And you also can put IPv4 addresses into IPv6 packets. Talking about configuration and standard daily use of IPv6, the question is, how do you use those large, painfully large and long addresses with in a manual way? My first advice is, don't do it. Just get to grips with DNS and other schemes of automatically assigning names to addresses and use them. But in the deployment phase, in the beginning, you will be forced to do so. So you write them down if you want to direct your browser to an IPv6 address. You usually have to enclose it in any brackets. because it was not so wise to use the colon as a separator between the blocks, because in browser context the colon is also used to designate the TCP or UDP port. So you have to use this. If you're scripting or programming, don't try to create regular expressions matching IPv6 addresses. You won't really manage it in a reasonable time. Use libraries like I've got a system administration background. I know Perl quite well. So in Perl there's a library called NetAdder IP where you can just start syncing. System answers this is a valid IP or legitimate. Very important point, speaking of auto configuration, is that auto configuration IPv6 is done by SMP. This does neighbor discovery, so the nodes ask who's around them. This does the auto configuration of the networking, default gateway, subnet mask, DNS, all those sort of things. And it just works out of the box. If you plug IPv6 and input devices together, they just start auto-configuring themselves as long as there is one router in the network configured to do so. Yes, there are several things done, like in IPv4, ARP is a very important protocol on this layer. This is also done by SMP v6 now. And to sum it up, I stated that IPv4 wasn't designed with security in mind. IPv6 was from the beginning, so it's very important for the Internet of Things. One of the forces that devices can trust each other. So you need encryption and you need authentication. This is also, these are building blocks of IPv6. And this has two consequences. The first one is you don't have to care about how do I enable my devices with IPsec. If they are IPv6 devices, IPsec is built in. And the bad news is if you think your firewall is a tin box on the parameter of your network, you've lost because you lost the parameter. We're talking of globally addressable devices around the world. So there is no really perimeter to your network anymore. Well, I didn't quite rush through all my slides, but I think I'm yes. So thanks for listening, and now we've got some time for Q&A.
Okay, any questions?
Did I understand correctly that all functionality of DHCP is now integrated in ICMP?
Yes, basically all you can do with DHCP and IPv4 is now done by so-called stateless auto-configuration via ICMP v6 packets, but there's still DHCP v6, so you can still use DHCP. Stateless auto-configuration does not care about which device gets which address or which device is allowed to use your network. If you want to have control over this, you still can use DHCP and turn off stateless auto-configuration for your network. Further questions? So, I did wipe out any clarity.
No questions anymore. Okay, who has understood what he has told us? Okay.
Thanks for being so polite.
But it's not his fault. Okay.
But I have another question.
Okay.
A typical routing table and adding routes to the table is done very similar to IP version 4 or?
Yes, there are the major routing protocols are ported to IPv6. Of course, tables are at least 4 times bigger. But yes, the border gateway protocol works after some patching. RIP and G works again. which is very handy for small networks because it's got low overhead. And yeah, well, all the major routing protocols work just like they did before, only the routing tables are quite large.
Another question. I noticed that there was this anycast functionality, and you mentioned the example with the time service.
Yes.
I think it's extremely security relevant to have someone answering the queries that you put in the network. What is the IP version correct way of dealing with security? So that I guess answers on maybe a particular subnet or whatever.
Yes. There are very beautiful ways to attack a network by spoofing time service packets and by poisoning DNS. The answer from theory would be use IPsec, at least use authentication. Use the authentication header to make sure that the answers you are getting come from the system you expect. This in daily life, this can be painful because you have to deal with the public key infrastructure, and you have, or at least with distributing pre-shared keys for the authentication. But this would be the most secure answer to your question. There's no easy way to tell devices to just listen to certain name servers besides enabling authentication. So at least I do not know of a standard way for configuring. Besides, of course, doing so by on the device to configure some blacklists or something, whitelist tables. But this is cumbersome, not feasible, at least in the Internet of Things context. I don't want to configure 500, 400 devices in my house to use just my time server. But I could automatically distribute the necessary key authentication information to the host to use IPsec. You need not use encryption using IPsec. You can rely on authentication. And for DNS and time service, encryption is nice to have, but it's not necessary.
Okay. But this authentication is made on other levels of infrastructure, or it is directly supported by IP things. Authentication header
Yes.
Yes.
The authentication header works just if you're familiar with IPsec, then it's just like we've done with IPsec for about 15 years or so. The clue with authentication is, as I mentioned, the key infrastructure. You have to have. It's the same problem like the chain of trust model, for instance, with SSL certificates on web servers, with HTTPS. The problem is the same. You need some trust anchor anywhere. Is it a manually distributed key pair, or is it be it a public key infrastructure? You have to have some kind of trust anchor. Solve this problem. All your devices can use this trust anchor, and you just have to tell them once which certificates to trust and which not. For instance, if you do certificate-based authentication like in HTTPS, and then the devices can automatically choose which answers to trust and which not. Did this answer your question? I'm not quite sure.
I think that yes, there is a SSL protocol, or this protocol which ensures security or exchange.
Well, yes, SSL uses the same cryptographical methods like IPsec does. Yes. It's comparable. It's not the same because IPsec does it on the transport layer. SSL does it on the replication layer. But from theory, it's the same. It's the same things. Yeah. It's the same cipher seals, key lengths.
Some standard protocol, yes, like handshake, handshake.
Yes.
exchange, and on the IP6 level, this is a standardized. Okay.
Yes.
Okay.
The difference is in IPv6, it's standardized on the protocol level. So if you claim to support IPv6 with your protocol stack, you have to support IPsec. You can't opt out here. With IPv4, IPsec is optional. It's not a part of the IPv4 protocol, which brings us to an enormous number of problems. If anybody is familiar with VPN configuration between vendors and so there's lots of implementation glitches. In IPv6, this should theoretically not happen because the implementation is really good for us. Okay.
Go ahead.
Is it possible to implement VLAN?
VLAN, virtual LANs on the Ethernet layer. Yeah, this is layer 2. VLAN is on the Ethernet layer. You don't have to. The VLAN tags on your Ethernet devices don't care about transport layer. If we rush to the beginning, VLAN tagging is done here. Of course, also completely transparent. Okay, you got another question?
My question is regarding firewalls. Do you have an overview how many commercial or public domain firewalls support IPv6 management?
I can't give you a very recent answer. The last time I talked to guys in the firewalling business about IPv6 was 4 years ago at the IPv6 Congress in Munich, and their answer to the question, how do you deal with endpoint-to-endpoint encryption, which is the big problem. If we use IPsec from endpoint to endpoint and there's a box in the middle, the packet inspection is useless because with strong encryption you can't decide what's within the packet. You don't even know which upper level protocol or port is used. And they just say customers don't need it. 4 years ago. I talked to 3 of the big ones who sell nice tin boxes with various colors, and they say customers don't need it. Customers don't need endpoint-to-endpoint encryption, so we don't care. I hope they changed their minds by now, but I don't know how they could keep up with their business model in a world where security moves to the very nodes on the system. You have to deal with firewalling on your node, on your PC, on your smart meter, on your whatever. And this is quite difficult if your business model consists in tin boxes with packet filters. This won't work anymore.
Okay, thank you very much. I hope you enjoyed the talk from Gustav. We will put the slides of his talks onto the Meetup platform so you can download it and read it at home. Now we will make, as every time, 10 minutes break.